We studied direct current earlier. Direct current does not change direction with time. However, most appliances in our daily lives run on voltages and currents that vary with time. A time-varying voltage that varies like a sine function is called alternating voltage or AC voltage, and the current driven by it in a circuit is called alternating current or AC current. The term AC is actually universally used to refer to any electrical quantity that varies with time, just like simple harmonic motion that is related by a sine or a cosine to time. In circuit diagrams, AC voltage is denoted by a sinusoidal wave in a circle. Electrical energy supplied to consumers is transmitted and distributed through power grids as alternating current. AC is preferred to DC mainly because AC voltages can be easily and efficiently converted from lower to higher voltages and vice versa using transformers. Let us study what happens when an AC voltage source is connected in series to a resistor with resistance R. The potential difference provided by the AC source is expressed as V is equal to Vm sin omega t. Here, Vm represents the amplitude of the voltage and omega represents the angular frequency of the oscillations of the potential difference. Angular frequency omega should not be confused with frequency. For example, the AC voltage supplied to our households has a frequency of 50 Hz. This means the angular frequency is 100 pi radians per second. We can calculate the current passing through the resistor using Kirchhoff's loop rule. The algebraic sum of all the potential differences across various components in the circuit is equal to 0. A proper sign should be used for potential differences around the loop. Applying Kirchhoff's loop rule to the given circuit, we get Vm sin omega t minus IR is equal to 0, where Vm is the maximum potential difference offered by the AC source. Here, Vm sin omega t is the potential across the given voltage source. The second term IR is due to the fact that if a current of magnitude I passes through a resistor of resistance R, the potential fall across it can be denoted by the term IR. Solving this equation, we get the expression for current as I is equal to Vm by R into sin omega t. As the magnitude of the resistance of the resistor R is a constant, the equation is simplified to I is equal to Im sin omega t. Here, Im is the amplitude of the current denoted by the fraction Vm by R. The graph of the current passing through the resistor and the potential difference across it against time is as shown. Here we observe that the magnitude of the current flowing through the resistor and the voltage across the two ends of the resistor reach their maximum values at the same time. They also reach their respective minimum values at the same time. In fact, these values even reach 0 at the same time. This implies that in a pure resistor, the current flowing through the resistor is in phase with the potential difference across it. The fact that the current and voltage are in phase can be seen more clearly if we divide the instantaneous voltage V by the instantaneous current I. Therefore, the ratio of the instantaneous voltage V and instantaneous current I is a constant of magnitude R. This means that the ratio of voltage to current is constant. Hence, Ohm's law is valid in the case of resistances connected in a circuit with an AC voltage source. As the AC current flow across a resistor varies with time in a sinusoidal fashion, its magnitude takes both positive and negative values. Here, all instantaneous current values over a cycle add up to 0. Therefore, the average current is 0. However, the average power across the cycle is not 0 since the power dissipated across the resistor is proportional to I square. As I square always assumes a positive value even when the value of current is negative, the average power is always positive. We know that electric current refers to the flow of electrons in a circuit, and the direction of the current is conventionally taken to be the one opposite to the direction of the flow of electrons. As electric current passes through a resistor, the resistor gets heated. This is due to the collision of electrons with other electrons and atoms, and the constant acceleration and deceleration of electrons due to a reversal in the direction of the flow of current. This heat dissipation across a resistor due to the electric current through it is also known as Joule's heating, which is expressed as I square R. The instantaneous power dissipated in the resistor is I square R. Earlier, we learned that the current through an AC circuit containing a resistor is given by I is equal to Im sine omega t. On substituting the value of I in the equation for power, we get P is equal to Im square R sine square omega t. If we average the value of the instantaneous value of power over an entire cycle, we can write the expression as shown. Here, the quantity P bar denotes the average value of power. Conventionally, an average of values is shown with the bar over the quantity symbol. The angular brackets denote the average of the quantity inside the brackets. As the quantities Im and R are both constant, we can take them out of the angular brackets while computing the average value of the expression. Now, we have to calculate the average value of sine squared omega t in order to compute the average value of the expression. For this purpose, we will use the trigonometric identity. Sine square omega t is equal to half of 1 minus cos 2 omega t. Therefore, the average of the required expression is given as shown. However, the average value of cos 2 omega t over a complete cycle is 0. This makes the average of the sine squared omega t over a cycle as half. Therefore, the average power dissipated over a cycle is half of Im square R. If we define a new value of current to be associated with AC, that is, Im by root 2, we can get the expression of power dissipated from a resistor in AC current in the same way as in DC current. That is, I square R. This new value of the current is called root mean square. In short, RMS current, denoted by IRMS or effective current. RMS current is defined as the root of the mean of the square of current. For a sinusoidal current, its value is 1 over √2 times or 0.707 times the amplitude of the AC current, Im. The average power dissipated by any form of AC current in a resistor is IRMS square R. Similarly, we can denote the RMS voltage or effective voltage, VRMS, as Vm by √2, where Vm is the amplitude of the AC voltage. The value of voltage normally used to describe an AC voltage is an RMS voltage. For example, domestic supply has 220 volts AC. Here, 220 volts is the RMS value of the voltage given to domestic consumers. The amplitude of the AC is √2 times the value of RMS voltage. Thus, the amplitude of the AC given to domestic consumers is approximately 311 volts. In our study of AC current applied to a resistor, we found that the voltage and current through a resistor are in phase, which is not always true. That voltage and current through a resistor are in phase was based on an assumption that there are only resistors in the circuit. Normally, circuits are made up of inductors, capacitors, and other elements. To study such complex circuits, where elements other than resistors are also present, computing values becomes an arduous task. Thus, we use the notation of phasors, which significantly simplifies the calculations involved in solving such complex circuits. A phasor is a representation of a sine wave whose amplitude, phase, and frequency are time invariant. We can visualize a phasor as a phase vector that rotates about the origin with an angular velocity omega. Thus, the phasor of a wave is a vector that has a magnitude equal to the amplitude of the wave and that rotates around the origin with an angular velocity equal to the angular frequency of the wave. To get the physical values of the sinusoidal varying quantities, such as AC current I and AC voltage V, we take the vertical component of the phasors, I and V, respectively. The magnitude of phasors, V and I, signifies the maximum or peak amplitudes of the quantities specified by the phasor. However, the instantaneous projections of these phasors give the instantaneous values of the quantities that they represent. The phasors for V and I, in the case of a resistor, are always in the same direction. This means they are in phase, or the phase angle between them is 0. An inductor or a solenoid is an electrical component that can store energy in the magnetic field created by a varying current flowing through it. It is typically a wire wound around a ferrite core. An inductor resists any change in the current flowing through it. Any change in current through an inductor induces an EMF across it. This induced EMF is proportionate to the rate of change of current. According to Faraday's law of electromagnetic induction, the induced EMF in an inductor is equal to minus L dI by dt, where L is the self-inductance constant for the inductor, and I is the amount of current passing through the coil. This EMF opposes the change in current flow through it in accordance with Lenz's law. Hence, a minus sign as per convention. Now, we shall see how an inductor behaves when an AC voltage is applied across it. Let's assume that the inductor coil has negligible or zero resistance. This assumption is mainly so that we can observe how an inductor ideally behaves. Now, assuming the circuit to be purely inductive, we shall make use of Kirchhoff's loop rule. According to this rule, the sum of potential differences across various components is zero. The voltage across the source of alternating current is V equal Vm sin omega t, where Vm is the amplitude of the AC voltage and omega is the angular frequency and t is the time. Let this be equation 1. Applying Kirchhoff's law to the purely inductive circuit, we get Vm sin omega t minus L di by dt equal to 0. Here, Vm sin omega t represents the potential difference applied across the circuit, and the term L di by dt represents the self-induced EMF in the inductor. Thus, we get di by dt to be equal to Vm by L sin omega t. Let this be equation 2. Equation 2 is a simple differential equation. It tells us that the first derivative of the current with respect to time is a harmonically varying quantity with an amplitude Vm by L and an angular frequency omega. This implies that this derivative is in phase with the applied potential difference. Integrating equation 2 with respect to time, we get the value of the current in the circuit as I is equal to minus Vm cos omega t by omega L plus the constant of integration. Let this be equation 3. Since we know that the voltage source is supplying a time-dependent voltage, which is symmetric about 0, we can assume the same to be true of the current. Hence, we take the constant of integration as 0. Hence, equation 3 can be written as I equal to minus Vm cos omega t by omega L. Let this be equation 4. Writing minus cos omega t as sin omega t minus pi by 2, we get I equal to Vm by omega L into sin omega t minus pi by 2. Let this be equation 5. Now we substitute omega multiplied by L with XL, which is known as the inductive reactance of the circuit. We get the amplitude of the current Im equal to Vm by omega L or Vm by XL, since we know it to be the maximum current value attainable. Hence, equation 5 now becomes I equal to Im sin omega t minus pi by 2. Let this be equation 6. The expression we used earlier for Im implies that the value of current in comparison with the value of voltage is limited by the denominator, which we call the inductive reactance of the circuit. This by analogy for a simple resistive circuit can be considered an equivalent to resistance. This inductive reactance is directly proportionate to the inductance L of the circuit and the frequency of the current or voltage. Inductive reactance is equal to 2 pi LF, which is equal to omega L, since 2 pi F is equal to omega. On close inspection of the expression derived for the value of current in the circuit, we can see that the current lags voltage by a factor of pi by 2 in phase. The phasor diagrams to analyze the relationship of lead or lag between the current and voltage is shown. The current lags behind the voltage in phase by pi by 2 or in time by 1/4 of the time period t. Another observation is that the maximum value of the current in the circuit is achieved at exactly 1/4 the time period of every cycle. Let us now try to see the power dissipation through the inductor compared to resistance. The instantaneous power supplied to the inductor is denoted by the product of voltage with current flowing through any circuit element. By substituting for V and I as in equations 1 and 6, we get P is equal to Vm sin omega t into Im sin omega t minus pi by 2, which is equal to Vm Im sin omega t into sin omega t minus pi by 2. As sin omega t minus pi by 2 equal to minus cos omega t and 2 times sin omega t into cos omega t is equal to sin 2 omega t, we get power P equal to minus Vm Im by 2 into sin 2 omega t as shown. Let this be equation 7. This instantaneous power evaluates as a time-dependent harmonic function. As this is a time-dependent sinusoidal function, its average over one complete time period will be 0. The argument of sine function for voltage is omega t, and for power is twice omega t. Hence, the time period for the power function is half the time period for voltage. Since the average value of sine 2 omega t over one complete cycle is 0, the power supplied to an inductor on average in an AC circuit over one complete cycle is 0. This can be seen as displayed by the plot of power supplied versus time. Variation of voltage and current with time is also plotted on the same graph for comparison. As the inductor is nothing but a coil of wires, it is structurally the same as an electromagnet. Hence, when the current flows through the coil, it is magnetized and demagnetized depending on the direction and magnitude of the current in the circuit. Variation of magnetic flux with time too is plotted on the same graph. As shown in the graph, we will study the magnetization of the inductor in the 4 periods marked in the graph as 0, 1, 1, 2, 2, 3, and 3, 4 respectively for one complete cycle of voltage or current. As in the first time interval 0, 1, the value of the current keeps rising from 0 and reaches its peak value at 1/4 of its time period. The flux passing through the coils change, setting up a magnetic field as shown in the figure. The current enters the inductor coil at A and leaves at B. As the current and voltage are both positive. It means the power is positive. Positive power means the inductor is absorbing energy from the circuit. In the second time interval, 1, 2, the value of the current keeps decreasing from its peak value at 1/4 of its time period and reaches 0. But it always remains positive. The flux passing through the coils change, decreasing the magnetic field setup as shown in the figure. As the current is positive while the voltage has become negative, it means the power is negative. Negative power means the inductor is releasing energy to the source, which is the circuit. During the third time interval 2, 3, the values of both current and voltage are negative. Since the current has become negative in this interval, the flux passing through the coils change, setting up a reverse magnetic field as shown in the figure. In this case, the current enters the inductor coil at B and leaves at A. As the current and voltage are both negative, it means the power is positive. Hence, energy is being absorbed by the inductor. During the last time interval, 3, 4, the value of the current decreases and reaches 0. As the current is negative, while the voltage is positive, it means that the power is negative. Hence, energy is again being released from the inductor. This cyclic discharging and charging of the magnetic field of the inductor in reverse polarities keeps on taking place as long as there is AC current flowing through the inductor. Thus, the instantaneous power in the inductor is positive when both the instantaneous voltage and the instantaneous current are positive or both negative, and the power is negative when any one instantaneous voltage or instantaneous current is positive and the other negative. A capacitor is a device that can store a charge. A simple capacitor consists of two conducting plates separated by an insulating material called a dielectric. Unlike an inductor, which resists any change in current, a capacitor resists any change in voltage, thus ensuring a supply of constant voltage. Let us understand what happens when a capacitor of capacitance C is connected to a DC voltage source of potential difference V. When the key is closed, the capacitor gradually builds up charge as current passes through it. If the charge on it at this instant is Q, then the potential difference across its plates in the steady state is V is equal to Q by C. As plate A of the capacitor is connected to a positive terminal, positive charges accumulate on plate A. The positive charges on plate A repel the additional positive charges that the source tries to deposit on the plate. Thus, the capacitor resists the further build-up of charge on its plates. When the capacitor is fully charged, that is, the plates cannot take any more charges, the capacitor fully resists the current and the current in the circuit falls to 0. The state of a capacitor is known as a steady state. Now let's look at how a capacitor behaves if an AC voltage is applied across it. Consider a capacitor of capacitance C connected to an AC voltage source as shown. the instantaneous AC voltage, V, applied to the capacitor is denoted as V is equal to Vm sine omega t, where Vm is the amplitude of the applied AC voltage. Let this be equation 1. Now assuming the circuit to be purely capacitive, which means it has only a capacitor in the circuit, the instantaneous voltage across the capacitor is equal to the voltage supplied by the AC source. We shall make use of Kirchhoff's loop rule. According to this rule, the sum of potential differences across various components in the circuit is 0. Thus, we have V minus Vm sine omega t is equal to 0, which again leads to equation 1. As instantaneous voltage across the capacitor, V is equal to Q by C, we can write equation 1 as Vm sine omega t is equal to Q by C, or Q is equal to C into Vm sine omega t. Let this be equation 2. We know that current I is the rate of flow of charge in the circuit. That is, I is equal to dq by dt. Let this be equation 3. Substituting equation 2 in equation 3, we get I is equal to d by dt of CVm sine omega t. As C and Vm are constants, and as d by dt of sine omega t is equal to omega cos omega t, we have I is equal to omega Vmc into cos omega t. Let this be equation 4. By trigonometric substitution of cos theta with sin theta plus pi by 2, we get equation 5 as shown. This equation can be represented as I is equal to Im sine of omega t plus pi by 2, where Im is equal to omega Vmc. Let this be equation 6. The amplitude of the current, Im, can also be expressed as amplitude of voltage, Vm, divided by 1 by omega c. Let this be equation 7. Here, 1 by omega c is analogous to resistance and is called capacitive reactance. Capacitive reactance is denoted by Xc. Hence, this term capacitive reactance is denoted by the inverse of the product of angular frequency, omega, and capacitance, C. Let this be equation 8. From equations 7 and 8, we get the amplitude of the current, Im, as the amplitude of the voltage, Vm, divided by the capacitive reactance, Xc. On close inspection of equations 1 and 6, which are derived for the value of current in the circuit, we can see that the current leads voltage in phase by a factor of pi by 2 compared to voltage. The phasor diagrams for analyzing the relationship of lead or lag between current and voltage is as shown. This lead in phase by pi by 2 units is equivalent to a lead in time by 1/4 of time period t. Another thing to note is that the maximum value of the current in the circuit is achieved at exactly 1/4 the time period of every cycle before the maximum value of voltage is achieved. Let us now try to look at power dissipation through the capacitor compared to resistance. The instantaneous power supplied, P, to the capacitor is denoted by the product of voltage with current through any circuit element. Using equations 1 and 4 and the relation Im is equal to omega Vmc, we get P is equal to Vm sin omega t into Im cos omega t. Since sin omega t into cos omega t is equal to 1 by 2 sin 2 omega t, we get P is equal to Vm Im by 2 into sin 2 omega t. Let this be equation 9. This instantaneous power here evaluates as a time-dependent harmonic function. As the average value of sin 2 omega t over one cycle of AC is equal to 0, the average of power P over one complete time period will be 0. Hence, power supplied to a capacitor on average in a circuit is 0. This can be seen as displayed by plotting a graph representing power supplied over time. As shown in the graph, we will study the charging of the capacitor in the 4 time periods marked as 0-1, 1-2, 2-3, and 3-4 respectively. As in the first time interval 0 to 1, the value of the current keeps decreasing in the circuit from being maximum at time t is equal to 0 and reaching 0 at 1 at 1/4 of its time period. By the end of this time segment, plate A gets fully charged with positive charges and plate B with negative charges, and they oppose any further current in the circuit. The plates are fully charged at the instance 1. The voltage across the plates is in phase with the charge Q and peaks at time t is equal to 1. As the current and voltage are both positive, it means that the power is positive. Positive power refers to charging of the capacitor. Hence, power is being absorbed by the capacitor and it gets charged. In the second time interval, 1 to 2, the current changes direction. Thus, the accumulated charges on the plates reduce. The voltage reduces but remains positive. Since the voltage is positive and the current is negative, power is negative. Negative power refers to discharge of the capacitor. Hence, energy previously absorbed by the capacitor is now being returned to the circuit. In short, the capacitor is discharging in this part of the cycle. In the third time interval, 2 to 3, the value of current keeps increasing. Here, as the current now is in the opposite direction compared to the last interval, the charges on the two plates effectively interchange. Plate A is now negatively charged, while plate B holds positive charges. As the current and voltage are both negative, power is positive. Hence, energy is again being absorbed in the capacitor and it gets charged. In the last time interval 3 to 4, the direction of current again reverses at 3. Thus, the charge begins to deplete from the capacitor plates, thereby reducing the effective voltage across the two plates. The voltage finally becomes 0 at 4. As the voltage is negative, while the current has become positive, it means that the power is negative. Hence, energy is again being released from the capacitor. Thus, finally at the end of the cycle, the capacitor returns to state 0 again. This cyclic discharging and charging of the capacitor, or more precisely, its conducting plates, in reverse polarities keeps taking place as long as AC current is established in the circuit.